So these are for problems number 37 through 40. This is an example. Water is flowing into a cone-shaped tank point down at a constant rate of 3 cubic meters per minute. The cone is 20 meters tall with a radius of 8 meters. How fast is the water level rising when it is 5 meters deep? So I drew a sketch over here, and you don't have to draw it as exact as this. You can just sketch it out real fast, but here's my cone. And you can see it's 20 meters tall. The radius is 8 meters. We're pouring water into it. And this would be wherever the water level is. We have these little cones that are constantly rising. So as you pour it up, if you just looked at one moment, we'd have a little cone here. A little later, it'd be a taller cone, until it's eventually 20 meters. Okay, and we want to find out how fast this height here is changing at a certain particular height. Okay, how fast it's changing. So let's take a look at it. We have 3 cubic meters. So let's look at what we have. We've got 3 meters cubed per minute. So this is going to be a volume. So this is going to be my dV dt. Meters cubed is volume. So we'd say that dV dt equals 3. That would be meters cubed. Okay, and how fast is the water level rising? So we're looking for dH dt. This is the height. We'll see how fast this is changing, or what dH dt is. That's what we're looking for. When the height actually, because it's going to be changing, because remember we talked about this before in class, the lower it is, the faster it's going. As it gets higher, it starts going slower. So when h equals, what? 5 meters, 5d. Okay. So when h equals 5, so again we have to go to our formula for a cone. For the volume of a cone, volume equals 1/3 base area times height, which is 1/3 base area is a circle, pi r squared h. And we want to get our derivatives in, so we'll take the derivative of this, except we can't take the derivative because we have 2 unknowns. So what are we going to do here? Well, we're going to have to use the fact that these are similar triangles. These cones here are similar cones. They have the same shape, just different dimensions, but they are basically similar, because if you look at these triangles and this relationship between h and r, we see that this triangle, this right triangle here, which represents part of the big cone, is similar to this small right triangle, which represents the always changing cone, because we have an angle. Right angles are both triangles, and then this angle is common to both. So by angle, this right triangle, the big right triangle, is similar to the small right triangle. So that means the ratio of the corresponding sides are the same, and that's how we're going to get a relationship between r and h, and then that's going to be like a constraint that will help us reduce that. All right, so what do we got? We have to take a look at this, and big triangle to small triangle, so I can say 8 over r equals 20, big triangle to small triangle, 20 over h. So big triangle to small triangle, big triangle, 20 to small triangle h. So that's our proportion. These two ratios are the same because these triangles are similar by angle. And then I can just cross multiply, so I get 8h equals 20r. And I want to reduce the r because I'm looking for dH dt, so I want to get r in terms of h, so I'll just divide by 20, so I got 8h over 20. And I can reduce that to be 4h over 5. I'm sorry, 2h. Excuse me. 4 goes in there twice. 2h over 5. That equals r. 4 goes into 8 twice. 4 goes into 25 times. So that's what we've got. 2h over 5. That equals r. So every time I see an r, I can put 2h over 5. And then I'll be able to get this into one unknown. Then I can take the derivative. So volume equals 1/3 pi and then r squared h, and my r is the 2h over 5. And then we'll square that. And that's going to be 4h squared over 25 times h. So y equals, put this over here, 4 pi and 3 times 25 h cubed. And I'll take the derivative. Now, and I've got it in terms of one unknown, and I can take the derivative. So this is a good mathematical model for this situation. And we have this relationship between the radius and the height. And then that's going to be, this is all constant, so we leave that out front, 4 pi, 3 times 25. And then when I take the derivative of this, I'm going to get 3h squared times dh dt, because we're taking the derivative with respect to t time. The reason why I left this factor 3 here is because 3 over 3 is 1. And I can substitute my values, and I have dv dt, which was 3. And that equals 4 pi over 25 times h squared and dh dt. And what was h? H was 5. Well, this works out again nicely because h up here was 5, so I put 5 in here. And what's 5 squared? 25, so 25 over 25. That works out a little bit easier. They don't always work out so easy, but in this case they did. Maybe that's not a good example because they do work out nicely. So if I divide both sides by 4 pi, I've got 3 divided by 4 pi, and that's going to be in meters per minute. And that equals dh dt. Now if this didn't simplify out, then you would just multiply both sides by 25 and divide both sides by whatever this is, and then you could simplify. So you might have a little bit more challenging arithmetic. I guess I didn't do that on purpose. I just made these up real fast. It just happened to work out like that. So that's nice. So that's your dh dt, and that's what you're looking for. How fast the water level is rising when it is 5 meters deep, 3 over 4 pi meters per minute. It's not very fast, but we're not putting it in very fast either because we're just putting in 3 cubic meters per minute, so that's not like a lot relative to the whole thing. Okay? And like I said, again, if these are different numbers, just if this was like 6, if there was 6 at 6 feet, then that would be 36 over 25, so I'd have a 25 over here and a 36 over here. And you could do some simplifying, so kind of be aware of that.